Okay, happy to present Andrea Bolamperti today. Andrea got his PhD at the University of Padua and then moved to Munich, where he's now an MPIA fellow. Andrea worked on many different topics, from gravitational lensing and the modeling in particular to high redshift galaxies, star-forming regions, and today we'll talk about investigating the properties of the circumgalactic medium through Lyman alpha polarization. Yeah.
Thank you. So thank you for the introduction and for being here. As Anita mentioned, I'm talking today about. Anyway, I'm presenting one of the last projects that I did during my PhD that I did between the University of Padua. This project was done between the University of Padua and ISO. And the results that I'm showing you today have been published some months ago in this paper, where you also can see people from these institutes as Anita and Eros. So the idea behind this paper is a bit something that is new, because it's based on the Lyman alpha line. So the Lyman alpha line is a resonant line. So every time Lyman alpha photon is emitted, it experiences different scatterings with the hydrogen particles, and the resulting frequency and direction of these photons depends on several properties, like the H1 column density, so the density of the hydrogen that are responsible for the scattering, the kinematics of this medium, and the geometry. Also depends, of course, on quantum mechanical probabilities, the different energy levels, and the region from which the photons are emitted. So the idea is that we are collecting an ensemble of photons, so we are not observing yet individual photons. And given that exactly we are observing an ensemble of photons, we are not directly measuring the scattering events that are affecting one photon, but instead a population of photons. So if we suppose that the photons are created in the center, so there is an emitter of Lyman alpha photons, this photon can undergo different scatterings, but if they scatter in a medium that is symmetrical, there is no preferential direction from the scatterings. So what we observe is a polarization that is very low. On the other side, if there is a preferential direction for scattering, what we observe is that there is a preferential direction. So we observe a polarization that can be as large as more than 50–60%. Another in the case in which the photons are emitted from the center. Another scenario is the one where the photons are emitted from an extended region, maybe due to the star formation or fluorescence. And in that case, for example, given that the formation is more extended, the number of scatterings is reduced, so we observe a lower polarization degree. So this is the idea behind this study, and the Lyman alpha line for the moment was only studied through the spectral and the surface brightness profiles. And the main way it is studied is through radiative transfer models that have been developed. The problem is that different models predict very similar spectra. So you see in this panel, for example, from the work of Heide et al. In 2018, two different cases, two different geometries for the CGM, so the hydrogen, the medium where the scattering happens. And on the left, you can see an ellipsoid with different outflow velocity, with different colors. And on the right, a completely different geometry. So the photons are created in the center, and then there are two broadening jet angles with different apertures that you see with different colors. What you can also observe, if you consider, for example, the yellow lines from the two models, it's very difficult or impossible to distinguish them from observational setups. They are very similar, but they have very different polarization profiles, as you see here. And the reason, for example, in this case is the one I was mentioning before. So, for example, in the second case with the jets, the system is highly asymmetric. So you can see that in particular on the tails, the polarization can reach values of 60–80% of polarization, while in this case it is more symmetric. The polarization remains very low, below 20–30%. So observationally, the way we measure polarization is to use a superachromatic half-wave plate mosaic, where the light, where this schematic figure, the light is approaching with two different orthogonal polarization. Then after that, there is a prism that is separating the ordinary and extraordinary rays. And these rays have orthogonal polarizations. So in principle, we can rotate the mosaic by 2 angles to disentangle the two different rays. But given that the different observation have different gains and also observational constraints, at the end we have to measure with 4 different angles to obtain unbiased results. So the setup of the observation is similar to this one, where you see different slits. But I highlighted 2 slits because these 2 slits are covering the same part of the sky. So one is the extraordinary ray and the other is the ordinary ray. And by comparing these 2 spectra, we can measure the Stokes parameters, and then from that the polarization signal. So, okay, observational is very complicated to observe such a system, because given that you have to split the signal in 2, and also you need very large signal to noise ratio to obtain a large signal to noise ratio polarization. To give you an idea, to have a signal to noise ratio of 5% in polarization, of 5 sigma in polarization, you need images with the signal to noise of 35-40. So it's very difficult to observe such systems. And in fact, just this is essentially all the literature that we have on the studies of polarization of Lyman alpha. And all of them target these very bright objects like quasar, the galaxies, or these Lyman alpha blobs that are extremely luminous. And also their shift range, you can see, is pretty limited between 2 and 3. And so we have less than 10 objects, and none of them is a star-forming galaxy at intermediate redshift. So we decided to try to observe this typical star-forming galaxy at cosmic noon. And the target we would choose is this Abel 2895, sorry. And this is a galaxy that is strongly lensed by this cluster of galaxies. You can see the BCG in the center here. And there are 3 multiple images of this galaxy, M1, M2, and M3. This is a lens with a magnification factor of 5.5. The redshift is 3.4. And it has different, you can see here in the UV, it has different star-forming clumps that you can see in these res frame UV images on the bottom. Also, it was observed with thanks to the Lyman alpha. It's a Lyman alpha emitter. You see here the Lyman alpha contours for the 3 multiple images. And the Lyman alpha peaks are shifted with respect to the UV continuum. You can see it here, and the centers are here, while these blue and red contours are from a previous study from Eduardo Iani in 2021, and they are the lines from H-beta and the oxygen lines. So we have a large set of ancillary data on this system, so including Muse and Symphony, and it was also observed with ALMA very recently at the end of last year. And in ALMA, there is no detection of the dust continuum, while there is detection of C2 emission. And you see that different clumps and were identified, and the 2 of them are in the same location of the clumps we observe in the stuff in the res frame UV. So, but these galaxies has a very low, very small fraction of dust that is was observed both from the very steep UV slope of the spectrum, but also from the non-detection of the dust in ALMA. So what we added is these 18 hours of force 2 in the polarization mode. As I mentioned before, it's a very demanding observations. It's 18 hours, but thanks to the magnification factor of 5.5, it's approximately 450 hours without strong gravitational lensing. So we really need to go deep in this observation to be able to measure the polarization. And it is what I was mentioning before. So we have the 2 slits for the ordinary and extraordinary rays, where you can see exactly here the 2, essentially these 2 blobs are these 2 peaks here. And they are taken with 4 different observations. That is the number of different orientation that we need to completely cancel the biases in this study. So by combining all these 4 data, so we extracted the spectrum of the Lyman alpha line for this system, and we measure from comparing the different ordinary and extraordinary rays, and also the different degrees angles for the from the plate. We can measure the Stokes parameter Q and U, and from that the polarization. So these are the upper limits that we can put on the polarization of the Lyman alpha. But actually, in this you can already see here that both of the multiple images that we are considering here, we target the two of them. So this is the slit that we put in force, are very close to the BCG of the cluster of galaxies in the center. And you can see also some features here of the BCG. The point is that the light of the BCG that is included in the slit is diluting the polarization factor. So we had to remove it before measuring the polarization. So after removing the contamination from the BCG, you see here that the continuum now is approximately 0. The upper limit is less stringent because we have to correct for the dilution. So we have one single bin in the center of the Lyman alpha line, and that is approximately 4.6%. So an upper limit for the line of less than 5%. To interpret these results, we developed the radiative transfer models. The code that we use is this RT-SCAT code. And what we assumed in this case, we don't have spatially resolved information, as you can see from the data. It's very hard to resolve both of them, so we integrate over the entire both of the multiple images, so we don't have spatial information. So we choose this simplified model that consists of a central source of Lyman alpha photons and with two biconical winds. So the parameters describing this model is the width of the emission of the Lyman alpha photons in the center, the column density of the hydrogen in the winds, and the expansion velocity of the winds. And then there are two angles that are the opening angle of the wind. So it's from 0 degrees, that essentially is no aperture, from 90 degrees, that is a shell, and the line of sight angle. So from fitting the spectral shape from used data, and then we repeated it with forced data, we measured and fixed this parameter for these three parameters on top. And we explored different possibilities for the aperture angle of the wind and the line of sight. So the aperture angle is from 0, as I mentioned, to 90 degrees. So we have 7 different aperture angles with step of 15 degrees. While for the line of sight angle, we simulated from observing in the direction of the jet, so it's 0 degree line of sight to 90 degrees. So observing in this equatorial view, so observing directly to the source, perpendicularly to the wind direction. I wanted to show you how we fix this parameter. So this is the fit that was done on the Lyman alpha line of Muse. You see that the spectral resolution of Muse is lower than that we have now with force. But it's interesting to understand what's happening if we change this parameter, how we constrain them. So for example, in this case, the observations are this black dot line, and you see 3 different sets of model of simulated Lyman alpha profiles. And in this case, it's changing the aperture angle of the wind. So with an aperture, a width of the central source of only 100 kilometers per second. And you can see that none of them can reproduce the shape of the Lyman alpha that we observe. So we have we also have for some cases that the blue peak of the Lyman alpha is not suppressed. So this double peak structure, while on the other case, increasing it to 150, that is the value that we assume. In particular, for large opening angle of the wind, the blue line is very similar to our observations that are still the black dot line. And another important aspect that is also important in the following is the trend with the line of sight angle, because as you can see here, the Lyman alpha line that we observe is shifted with respect to the systemic velocity of 0 kilometers per second by approximately 400 kilometers per second. So in order to reproduce this shift, a scattering component is needed. So you can see in this case, for example, that if we observe the opening angle of the wind is 60 degrees. So if we observe from 0 degrees, so in the direction of the jet, the contribution of the photons that actually scatter, because we are observing in the direction of the jet, is the one dominant. So the spectrum that we observe from the Lyman alpha is shifted, and we can reproduce the shift of 400 kilometers per second. On the other hand, if we assume a 90 degrees line of sight angle, so we are not observing now in the direction of the wind, but instead we are observing directly into the central source. So the majority of the photons that we observe are not scattering in the wind, but are just undisturbed coming to us. So these photons are, by definition, they are not exactly centered on zero, because some photon is still experiencing scattering, but most of them are not. So that's why we can by observing not in the direction of the jet, but directly in the center, it cannot reproduce the shift that we observe with respect to the systemic velocity. And this is a major aspect that we found in our study. So this is a figure that is collecting all the main results. So in black, you see the spectrum, the observations. So there is the spectrum on top and the polarization upper limit on the bottom. And there are 7 different panels for the 7 different opening angles that I show you here. So for what I've said so far, for example, in the 0 degrees and 90 degrees cases, the polarization is always 0, because these systems are by definition completely symmetrical for any line of sight. So the polarization is, by definition, is 0%. So in these two cases, we have 0% of the polarization. But if we observe for opening angle of 90 degrees, that is at the end an expanding shell, the photons are scattered. So the shift with respect to the systemic velocity is well reproduced. So the shape is not optimal, but the shift is well reproduced. While if the opening angle is 0, so no scattering is happening, the shift is not reproduced. So in this case, we cannot reproduce the shape of the Lyman alpha line. And we can do it with different angles, with different line of sight angles and different apertures. So in the case of 15 degrees, so now we have still a small aperture angle for the wind. And you can see that if for models that have a line of sight angle that is larger than 15, 20 degrees, so all these models here, essentially we are observing again directly to the center and not to scattered photons. So the Lyman alpha is centered on 0. While if we go to 0, 10, or still 20 degrees, the contribution from polarized observation for polarized photons is increasing, and the shift is well reproduced, even if also in this case the shape is not reproduced. In this case, the polarization is still consistent for all the line of sight, because the system is still pretty symmetric. So all the polarization are below 4%, and that's consistent with our observations. The situation is more interesting and changing here, for example, for 45 degrees. So we are in this situation here, for example. And in this case, the situation is a bit different. The idea is the same. So the models that directly observe in the direction of the center cannot reproduce the shift. So essentially are ruled out by modeling the spectrum, while in the other case, all the others can fit very well the spectral shape. And here, this is an interesting case where the polarization is playing a major role, because even if some different models can reproduce the spectral profile of the Lyman alpha, not all of them are consistent with the observations, with the polarization observations, because if you observe with an angle that is 30, 40, 50 degrees, so very close to here, the system is highly asymmetric. And as you can see here, for example, the 60 and 50 and 40 are all of them predict a polarization that is larger, also by factor 2 in this case, than the polarization upper limit that we measure. So in this case, the models that have a polarization that is consistent are those ones with small opening angles. So the ones for which the system is still pretty symmetric. So we can do, I'm not going through all of them, but the idea is you got it, is the same for all these cases. So we can summarize this plot is in just one single plot, that is this one, in which we have the line of sight angle in this case. So going from 0 degrees, so observing in the direction of the jet, to 90 degrees, so observing in the center. And here is the opening angle scheme with this different layouts. So from the top rows of before, so by fitting the spectral lines, all these models in black here are ruled out by the fitting of the line because they cannot reproduce the shift with the systemic velocity. And you can see that all the others that are in from gray to this white here can reproduce the shift and then can reproduce more or less well the spectral shape. So you see that, for example, 90 is gray because the line is not, the chi-square is pretty large for the discrepancy in this region, while some idea in this other case is much well reconstructed. So this is a chi-square is a metric to understand how much are in agreement there on the spectral shape. And by adding, we can add to this the constraint from polarization, and so they rule out this region. So the first important thing is that, as you can see, by studying the spectral profile, we can cancel things in this direction, while with polarization, we can go in the other direction. So the constraints we can put from polarization are actually complementary to those we can put from more standard and more present in literature, also studies from the spectral profile. And there are different models. There are those here that are white, but in shaded red, that are cancelled, that are not excluded by typical studies of the spectral profile, but are indeed cancelled from the polarization, the 1 sigma level in this case. So to try to put it in a context, as I mentioned, there are two main photon production mechanisms in high-redshift galaxies. And the first one is hydrogen recombination in a full ionized medium that is on large scales, and it predicts lower polarization fractions. And the second one is the in situ production. So the Lyman alpha are created by a central source, and then the photons escape the production site after different scatters in the surrounding H1 cloud. And the polarization of the signal we observe, it depends on the kinematics and the geometry of this H1 cloud. So given that we measure a low polarization, the polarization constraints are consistent with no scattering or scattering in a medium that is fairly symmetric. So given by both from the opening angle of the wind or from the line of sight angle. But it's also true that we need a scattering contribution to model the total intensity. So it is cancelling essentially the scenario in which there is no scattering. Yeah, so it's I wanted to go just through the summary and conclusion about this. So we are studying for the first time the Lyman alpha line for tracing the scattering minimum of high-redshift star-forming galaxies. So not extreme environments like quasars or AGNs, but typical star-forming galaxies. The polarization represents a complementary constraint to this, and it's observationally very demanding, and there are not a lot of systems that can be observed for this. Also, in this case, it's difficult to put it in a larger context because it is actually the very first system with this kind of study. But for this system, we measure an upper limit on the polarization of less than 5%, so we can put pretty strong constraints on the geometry or the line of sight angle for this object. And yeah, so this is consistent with scattering, not scattering, but not consistent with the first part, or scattering in a medium that is fairly asymmetric. And we also know that by combining two different probes, we know that a scattering contribution is needed to reproduce the spectral profile. Yeah, so that's all.
Questions for the speaker? Yes.
So you said that in the case in which the medium is very asymmetric, it can have very high percentage basically of. But according to your model, in which you have a biconical outflow, you never reach more than 7% of polarization level. If you go back to
yes.
this one.
Okay, yeah.
Or the 10% maybe. So is that the maximum polarization level you can reach according to this kind of assumptions?
Yeah, it's also true in comparison with the very first plot that I show where we also have 60 and 80%. The point in this case is due to the problem is also the contamination from the BCG that we had to subtract, because also in the plots, the 60-80% polarization level that we observed was not at the center of the line, but actually on the wings. So in our case, we had to essentially have just one beam for the entire. Actually, it's visible very okay. It's clear here. We only have one. We try to fit the line with also measure the polarization in these two parts, so in the outskirts, but the signal to noise is not large enough, and actually most of the contribution here is from the BCG, so it's subtracted after it. So we lose these constraints go to 80-90%, so we cannot use them to constrain the polarization level. So at the end, we have just one beam for enough signal to noise. So the signal to noise is actually low in the center. Let's go to the very beginning. Yeah. Also here you see that in the center is no more than 10% also here, and then it explodes in the wings. So
yeah. I was talking more about the models actually, that okay. they predict the level of polarization.
Yeah, the models can predict up to 60-80%, but in the wings. So okay. Yeah, exactly. So it's not. Yeah, I didn't. Yeah, sorry. Exactly. So if now I'm just showing the models in this region, but if you take the models here or let's say 1,000 kilometers per second, in that case you have larger degrees of freedom.
Because the biggest of them get scattering.
Yeah, exactly. Yes. Yeah, and also there are different contributions of scattering, and the scattering at 90 degrees is created less polarization than the one at 90 degrees. Then the essentially 480 degrees. So yeah, it's.
Yes, that's the curiosity. So what are the perspectives for having a larger statistics for this kind of studies? Because I understand it's pretty difficult job to get all this information out of the observations. So is it possible to?
Yeah, there are some systems that we can use to increase the sample. There are systems similar to this, so we can just including more statistics. We still need at least not strongly lensed, maybe a magnification factor of the order of 5 is the best to keep it simple. We actually tried to observe a system that was strongly lensed to gain what is missing in this study, that is the spatial resolution. The point is that the time you need is very, very large. So we asked for almost 50 hours. It was actually approved, but then they couldn't schedule it. But yeah, so the problem is always the time that you need for observations. ELT can help, but ELT will have so many deflections, so many reflections, because we have 3 or 4, not 5 mirrors, but they are developing a polarimeter for ELT, so in this case, yeah.
So towards the end, you you draw implications of your modeling, like absence of scattering, if I understand correctly, etc. Based on the physical modeling of these high redshift sources, what is more unexpected? I mean, would everything be compatible with what are the physical modeling of these sources, or something is more unexpected than something else?
Yeah, in this study, the idea is that for decades we have used the shell model for interpreting the Lyman alpha spectral profile, because actually we are not sure how these galaxies at high redshift are. So also this model is with the biconical outflow is pretty generical, because given that we are changing two parameters and also the line of sight angle, we can explore a different variety of parameters. But in this case, in particular with low polarization, so working with upper limits, it's very difficult to disentangle between, for example, the production mechanism of the Lyman alpha. So we can assume in this case that the photons are created in the center, and in that case, given that we can put some constraints on the geometry of the medium. we can, for example, that's another reason why we wanted to go spatially resolved, because in this case we cannot resolve if there is no polarization for this, or because the
no, I understand. What I meant is that beside the a posteriori model you can do, are there also attempts to physically model this object that would, for example, expect? I mean, are there physical models that try to produce these from first principle, galaxy formation, numerical simulations, etc., or is still?
Yeah, I think I would say it's still at the beginning. There are some models doing it, but also in for example, in the first reference that I show, in that case, they assume different geometries and then try to interpret them in light of, for example, this star-forming region can have outflows. We have evidence for outflows. So if you observe observe something that has outflows, this is what is expected. But yeah, it's still pretty uncertain. And that's why I think it's important to observationally rule out models.
Okay. Any other questions? Yes.
I may have missed it, but so you have more than one image of the galaxy in those. But how do you use the different images? Can you just sum the contribution of?
Yes, in our case, in the series there were two multiple images, so the third one is not included, M3. That is actually is the less magnified. So this, and we couldn't. We tried to perform the same study because in this case we extracted the spectrum including both A and B. So just summing up on the two of them. So the aperture is 7 seconds approximately. That we tried to perform the same study by extracting the spectrum of only one of the two multiple images, and we have consistent results. So the upper limit are less stringent, but instead of 5%, we have from 88 to 10% upper limits. So yeah, so the result is not given by the fact that we are observing two multiple images and just summing up.
Okay, then we can take the speaker again.